this section, I will do a little bit introduction about the track and ourselves, on also a little bit about the Women in Code study group, the study group. So my name is Karen Wong. I am a programmer at Research and Development Center. I'm located in Hong Kong, and we also have Chethana, who will be the speaker today. Chethana, would you like to introduce yourself a bit?
Hey everybody, thank you so much for joining. My name is Chethana and I am an associate software engineer at Realtor.com located in Austin, Texas.
Thank you, Chethana. And we also have Soumya on the from India. She is a final year of student from to do computer science. She and Stephanie have been the most amazing people to help us to get through this session, prepping everything. So now I'm going to use the chance to do a big shout out for both of them. So a little bit about Women Who Code Python track, in case this is the first time you join in. We are a group of Python enthusiasts who exchange their knowledge of Python and share their passion to help the community grow. We offer the series study group and workshop of like varying levels, from beginner to a very topic specific advanced events. And by the way, we are a very fun group. As you can see, like we are definitely having fun today, as usual. So for any future events, please check out the website www.code.com/python, and we also post all our awesome resources and materials on the GitHub link as shown on the slide. So a little bit about our study group. So we call ourselves a LeetCode study group. LeetCode is a website where it provides a lot of like awesome technical questions for software engineers, even programmers like me, to practice and get experience, because some of those questions are actually would be asked on a interview, where if you want to join in those like big corporate like Microsoft and Google. So the reason we created the group, because we want to solve a medium problem. Like we want to solve a medium level error problem together, because it's not as easy to do, especially by yourself, and go through the struggles and everything. It could be very, very discouraging. So the goal of each session is to recognize patterns of a specific problem and figure a strategy to solve it together. So the study group happens every other Thursday, and the Women Who Code Python track, and it will be at 8 p.m. Eastern time. So in case you're interested in joining in, feel free to join the fun group. We are an interactive section. I always learn a lot from Chethana and Soumya, so feel free to join us. All right, now we're gonna start for today's section, and I will hand it in to Chethana, the speaker.
Awesome, thank you so much, Karen. Welcome everybody to today's session, and if you're joining for the first time, welcome. Thank you so much for being here. Today we're going to be talking about the power of hash tables and how important they are when it comes to problem solving. So without talking too much, let's get into the session. Today's agenda is a brief discussion or a brief overview about hash tables, Python dictionaries, and Python sets. We're going to be focusing on dictionaries more, but we will do like a quick overview of all three of them. And after that, we will look at group anagrams. That's the problem we're going to solve within LeetCode today. We're going to start with some discussions, and then look at some test cases and talk about different approaches and time complexities and space complexities for those approaches, and we'll head on to a little bit of coding. And after that, we'll talk about what, based on what knowledge or anything we've gained from this session, what are the next steps we can, we can work on, what other problems can we tackle. So that's what we'll talk next, and then we'll end it with a little bit of Q&A. Also, disclaimer, I wave my hands a lot. I'm so sorry in advance. Okay, so let's get right in. Before we get into what a hash table is and all of that fun stuff, let's talk about this problem at hand. So from this snippet, what we can see here is we have a people array, an array that consists of tuples, where each tuple is a person detail, like a person. So like the first element of the tuple is the ID of that person, and the second element is the name of that person. As you can see, I'm super innovative with naming people. So P1 and PX, P of ID, whatever you want to say. So ID and then name. So we have it organized like this. The ... is for, we just have like 9 or something here. We can have millions, right? So yeah, that's what that indicates. So how do we, now that we've seen the structure of this, right? How do we access a person, a single person's name, maybe based on their ID? Maybe suppose I want to get the name of the person whose ID is 5. You could do that with the current way we've organized our data. We could do it in a single for loop. We could go over each tuple and check the IDs, see if see if anything pertains to, like, see if anything is 5. If it's 5, then we return. So we'll do 1, 4, 3, 9, and then we'll hit 5, and then once we hit 5, we know that this is the ID that we want, so we'll just return that. So that's what the snippet is. We can also see that you can't really it's not really sorted in terms of anything here. Like, it's not sorted in terms of ID. It's it's not, there's no sort of ordering over here. So you do have to go over every single entry. Okay. Fine, this looks fine for what we have. What about, like, in the worst case, if we're trying to find something, what would the time complexity be for this? Like, in the worst case possible, right? We'd have to go over the entire array. So that would be O of n, like a whole pass. Great. I do like our initial method of doing this. It seems super ambitious, but there are many other things that can change here. Like, if you have like we said, we have millions of records here, so our time complexity each time, in the worst case, it's going to be O of n. It would be like a full pass over the entire array. And what if we can just have like an ID and a person name in the way I've written it in the real world? We're going to have many more attributes to describe something. What if we have a lot of attributes? What if we want to get, like, I don't know, like maybe the age of a person with ID equals 6? You see where I'm going with this, right? So in that case, this is not really going to perform well. We probably, for this particular purpose, it's fine, but I'm trying to do a smooth transition here. Can we do better with how we organize our data? So drop in the chat, like, I didn't see the chat so far. So drop in the chat and let me know how we can store the data, like the people details data. Yes, awesome. Awesome. Yeah. So we could use because we're talking in terms of Python, we could use a hash table, or in terms of Python, a Python dictionary. Great. Now let's revisit the same problem from before. This looks super like it's just because we're comparing and we're taking in the, just transforming what we had before into what we want now. So we have now a people details dictionary with ID as key and the name as value. So the ID, it has to be unique. You cannot have duplicates. The key has to be unique. It cannot have duplicate values. And now accessing a single person's name based on the ID is a whole lot better, right? So we could just do people of, people is the name of the dictionary, people of that ID. It would return, it would look up for us, and the lookup time or the search time is constant. We'll discuss how it may be in the later slides, but so it literally transformed our game for us from that to this. Now I think we're ready to learn a little bit more about hash tables. Okay, so what we saw there, that was a Python dictionary. Python dictionary and a Python set, they're internally implemented using a hash table. So we should learn what hash tables are, because those two are inbuilt data structures within Python. We just use them, but sometimes it's good to know the basics before we get into it, in case you're feeling adventurous and want to try to implement a hash table. I don't know, just saying. So let's talk about hash tables. Three basic elements here. So you will have the key value pairs that you want, and then you'll have a hash function, and then you'll have an array. This is weird because but anytime we think of like a dictionary or something like that, we just think, okay, like immediately when we think of a dictionary, we think of like the curly braces and that's it. Like we don't think beyond that, but this is very interesting to know. So the key value pairs are going to be put into the array that you see on this end. And how do we know where to put each of that information? Like, for example, here we have name and age, right? So we take that pair of information, and where do we put it in the array? What decides that? That is a hash function. So basically, the hash function, it would take in your key, and it would return an index. And this index is where you put your key value pair from before. So like in this case, and how we write the hash function, that's a whole different session in itself. So we're just touching on a few important things here so that you can explore on your own as well. Okay, so hash of name gives index, great. So we have P1 and P2 here, very small data set, right? But for demonstration purposes, let's go with this. So hash of P1 gives you the index 1. Great, so P1 and 50 is the age, they're stored here. That information is stored in the array at the first index. And then hash of P2 is stored at the 0th index, great. So basically this forms the crux of a hash table. Now this looks super rosy and beautiful, right? You just like you have two indices, and then there's nothing weird happening here, where both those indices map to both of those key value pairs, they map to the same index or something like that within the array. Like the hash function cannot always like give you indices where you always don't end up in that situation where it gives you the same index for two or more records, key value pairs. So enough of the buildup. I'm going to talk about it now. Collisions. So this is super important to know because real world data is really messy, and you don't really have like it's not about the data, it's about the hash function here in general. So how how do you know if like your hash function is not going to give you the same index for multiple entries? So let's talk about this. In this case, you have P1, P2, P4, and P3. These are the names and then the corresponding ages. And let's look at what the hash function gives out in this case. So hash of P1, it spits out 1, great, no collision or anything there. And then hash of P2, it spits out 0. Okay, so 0 and 1, great. We only have like 2 from the previous slide. We only have 2 spaces in our array. Okay, so we come to P4. So P4 has an index of 1. It gives you the index 1, but P1 is already, P1 and its data is already in that index 1. Okay, we'll talk about this. And then same with P3, right? So it's like P1 and P4 and P2 and P3. Okay, so now we see that there are collisions here in this hash table. How do we resolve the collisions? Couple of methods. This is one of the methods to do it. It's called chaining. Basically, the collision that you saw before, it is sort of fixed by chaining them together as a linked list. What do I mean by that? So you initially start off with P150, and that would be within this the zeroth index in this array, and P2 and 20 first index in the array. Next, we come to P4 and 60, and that also has an index of 0. What we do here is we sort of point, we have a pointer from the 0th index to a linked list, where the head of that linked list is going to be the most recent collision that we saw. So what's the most recent collision for index equals 0, which is that is P4 60, that value. Just refresh P4 60, right? And then the same thing goes for P3 and 30, because P3 and 30, it sort of, oh, okay. So basically what I'm trying to say here is, it's the, if you have multiple collisions or anything like that, you chain them together, and the most recent collision will be on top, and that would be the head of that linked list. Okay, so this is fine, but there are some disadvantages to this. What do you think are some of the disadvantages for this method? Drop it in the chat. Ooh, nice. I love the chat. Everybody's so, wow, awesome. Okay, so yeah. Okay. Yeah. I love it. I love the answers that are coming through. Yeah, it's like, suppose your hash function is not the best, okay, and then for some reason it's not the best, and it's not doing anything to avoid collisions. It's just basically routing everything to the same index. Suppose you have a capacity for this array of maybe 100, and everything is being sent to index 0 or something like that. So you'll have a long chain there, like a long linked list there, and then the rest of it will all be empty. If you think about it, that's also another disadvantage, right? Like you basically waste a lot, and you also would need to look up, like you need to look through all of the elements in that linked list as you go on. So like to search or something like that. So it's 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 fine. It's fine for now. This is good. This is one of the approaches that we can try. But there's also another approach called open addressing. Yeah, so with open addressing, what do we do, right? So um, a way to implement open addressing, it's called open addressing, but what we do within it is we probe. It's called probing. We probe or look for empty spaces in our data structure when there's a collision. I'm going to explain to you. I'll answer some of the questions later at the end or like in the middle when we take a break. So let's talk about what probing means, right? So suppose our hash function, it returns index 0 for this particular 4 capacity array that we have here. And we're seeing that there's already something at index 0, right? So what do we do now? Linear probing, like the probing generally, what it does is from the point you're at, it checks the rest of the elements or the rest of the cells for empty slots. And another thing about open addressing is that you won't be using any kinds of extended linked lists or anything like that. This will just be your array. That's it. Like it would just be the key value pairs and the hash function and then the arrays. So the array. In this case, in the case of chaining, we also had a linked list to deal with the collisions. But in this, it's just going to be the array, right? So you start at index 0, and then you see, oh, okay, like this is full. What do we do now? Linear probing goes step by step. It linearly traverses along the array. So the next empty slot until it finds the next empty slot. So that's the ending point. So it goes to 1, it sees it's empty, and then it inserts there. This is for the second element. What about the third element? And the third element, like any other third element, which for which the hash function returns 0 as the index. That would if 0 is returned, it would come here. It would be like, okay, I need to look at the rest of it, right, to see where I can find the empty place or the empty slot. So it'll go here. That'll be 1, which is already filled, right? Like because we discussed that there was another element before this. So what it would do next is it would look again to the next element and be like, okay, this looks empty. This is an empty slot. So I'll insert myself here, or I'll put myself here. So yeah, and then the same thing happens on and on again. For every single entry that needs to be added to this hash table. And so the particular thing that we were talking about, that algorithm, it boils to this. It's called linear probing. It is we can describe it like this, in this way. J is the index, right? It's the index that the hash function gives out. So the index plus 1, I marked it as J, and the terms here you see here are a bit fuzzy because these are the things that were there in the CPython implementation. So anytime if you want to look back or something like that, this would be a good starting point to like explore those as well. So you have your index plus 1 mod size. So for example, the first time you come in, it's the first, the 0th index is filled, right? So 0 plus 1 mod 4. So 1 mod 4. So modulus, it returns the remainder. So it would be 1, right? You'd get back a 1. So that's where you need to be. So this is the empty slot, or this is the next place to check. So if you for the second element that you need to for which the hash function returns a 0, that would be here, right? And then the next step would be, okay, so 0 plus 1 mod 4. So 1 mod 4, which is 1. We go here, and then we see this is also filled. Then what do we do? Okay, so we're at the index 1 now. So 1 plus 1, that's 2. 2 mod 4, which is 2. So it has to go to the next index. It has to go to index 2, basically. So whatever this returns, that is the index you'd have to jump to. So this is very interesting, but also there are a couple of disadvantages to doing something like this. For example, if you're starting with 0, like we said here, and the hash function returns 0 for 3, for 3 key value pairs. Okay, so in that case, you'd probably fill up 0, 1, 2, 3, right? Like right next to each other, because linear probing. And for example, if it returns 15 or something later on, and then it returns 2 more based on 15, like it returns 15 for 2 more key value pairs. Then it would be 15, 16, 17. So like if you see here, there's like that huge, like it sort of groups things together. It sort of clusters them together. And this is like, it may or may not be good. Mostly, in my opinion, this is not the best, because you have clusters of data, and every time when you're going to look up the same data, like the same based on the key, you're going to look up the value again. This is for the insertion. We still need to look up, right, later on. So for that, it would still return 0, but then you'd have to check all of the other, like the elements right next to it. Like you need to traverse everything next to it. So it just feels like, okay, like until you get to that point, like where because you're storing your key value information in each of the cells within the array. So clustering really feels a little bit, it doesn't feel the best, but this method is much better than chaining. Both of them have a lot of like negatives to it, and they're almost constant time. That is, like, they would have like there's like mathematical proofs for this, in that there would be some extra constant space, or like some extra constant that we need to add into our lookup time or something like that. I'll make sure to like link all of those things, all of those explanations and stuff within our GitHub repo after the session's over. So okay, enough talking about linear probing and, whoa, all of its disadvantages and stuff. Python actually uses a probing algorithm that looks like this, the one right after this. So it's like the extra cruft you see, the 5 and something called perturb, all of that, they're trying to make sure that the randomness, or the information is equally distributed in the array. The key value pair information, it is equally distributed within the array. So that's why they've chosen to add things like this to sort of like mess up the usual flow, because here it's like, it goes right after each other. You'd probe or look right after, probing for empty spots or something right after each other. And this seems to be a little bit more different than what we were doing with probing. At least it would help with not clustering or grouping things together. So it would make sure that our key value pairs are equally distributed in the array, because at least it tries to do that. So what this means is, like, if we apply the same kinds of, like, this looks this this may not work with our like 4 element array capacity that we've decided, but it will definitely work for larger sets or larger array sizes. So if it's so J is the index again, and 5 times index plus 1 plus perturb. So this perturb variable is a hash code that Python generates, and this hash code at every iteration, it is right shifted by 5. It's super weird, but they're trying to improve the randomness of this, or like they're trying to make sure it's not it doesn't have the same issues as linear probing. So it can be like, when I say iteration or iteration, it's like when you suppose you suppose you end up at one point, then the next time you probably like if you end up there again, perturb would have shifted by 5, right shifted by 5, so it would land up at a completely different location in the array. Okay, so this is I'm not sure if this is like sort of broken a lot more understanding, or it gave you like some more thoughts to explore based on this. I think it's definitely fun to like understand these things more as we go on. There's one more thing we need to talk about before we talk about like other things like our problem and stuff. So a good hash function with all of this, a couple of things about hash functions are that, one, they need to make sure to minimize collisions. If it's not blatant, or like if it's not super obvious, more collisions is more problems and stuff. So you need to make sure to avoid, or like you can't really avoid collisions, you can maybe minimize collisions. So that, and they also have to make sure to distribute or to give out indices such that the key value pairs are uniformly distributed in this array that we're looking at. So those are like 2 important things that a good hash function would have. There are many more things, but like these seem to point out, these seem to stand out the most. Okay, so let's look a little bit at the Python dictionary and set. Like we're gonna be mostly dealing with dictionaries in this session, or like solving the problem based on dictionaries in this session. But we will look at a very, very brief introduction for a set as well. So a dictionary, like why we spoke about open addressing, why we spoke about hash tables and stuff. So a dictionary is implemented internally in Python using a hash table, and how the structure of it is that the key value, it has key value pairs where the keys are unique, and then it is ordered by insertion. What that means is it preserves insertion order, I think after 3.7 or so. So yeah, that's good. And with the set, it's the same thing. It's also implemented using a hash table. And here it's an unordered collection of data and has no duplicates. So yeah, pretty much the no duplicates thing, it has to it basically should not have duplicates, both of it. And at least in a dictionary, you can look up based on keys, but with sets, it may be different. The ordering technique that we were talking about before, I think it's mostly a dictionary. I think it's also a set, but like to get into the explanation a little bit more of open addressing, like I said, it's a whole other session, but maybe we can revisit it in the future or something. But yeah, so we have a people dictionary, and this is just like just an example to show the structure of a dictionary and a set. So we have a people dictionary. We have two keys and two values corresponding to the keys. Um, so and yeah, so people names is the set, and it's a set of names, people's names. And I have to learn how to name people better. This is pretty bad. Okay, so that's about it there. Um, awesome. So Python dictionaries, a little bit more. The insert, delete, and search times are all constant. Uh, Internally, how it works is it would we say it's a constant, it's an approximation. um there would be some other it wouldn't be variables that add up to the time. Like if you have variables, then they would make your time complexity huger, or like they'll blow it up or something. But if you have constants, like I don't know, maybe 100 or something like that, you know that they're like limited, and there's a limit to that extra constant that we add to the time. So that would still end up boiling down to constant time, because big O is upper bound, right? So yeah. And some of the ways you can use this, and some of my thoughts are, if you have like if you find yourself writing, I don't know, 3 4 loops or something, and like it's super convoluted. You're basically you're taking up a lot of time, but you could offset some of that. You could trade in some space for time. Then you can definitely use a dictionary, hands down. And if you if you're ever like, oh, okay, so I need to look for a value based on my key, or like I need to look this up and I don't know where to store this in, you're always have Python dictionaries as like the top of your choices of data structure when you're solving a problem. It always has to be there, like in your arsenal. So yeah, if you need to have a key value pair to easily look up values based on the keys, go for the dictionary. So the third one is more like a thought. Um, the more you do, the more you'll see, right? Like with most of these patterns and most of these things that we're learning, initially the worry is that, oh, when will I ever like get there? Like when you see more, it automatically, I like, trust me on this, like as you look at these kinds of problems more and more, solve more of these, you'll naturally get that kind of an intuition. It happens with every data structure and every algorithm. You literally end up finding that template or something in your head, and then you start doing it that way. Or your brain looks for these connections, and you'll get there. Definitely you'll get there. Awesome. So um there's also that like within a dictionary, you'd also just, if you want to like recompute the value based on the key and then like push it back, you can still do that with the dictionary, right? You don't like the values you can change, the keys you cannot. That's not ideal. So yeah. Okay, awesome. With that, um I'm going to take a quick water break, and you should as well. And if there are any questions or something like that, please drop the chat, or either Sami or Karen will look at it. Or yeah, quick water break.
Thank you very much, Chana. While you got you out, Chethana has a quick water break. For those of you who's the first time joining, we will be switching to the live coding session after the break. Before that, just want to say quick shout out to everyone who's very, very interactive, helping each other, solving the problem. It's been amazing. The chat is an amazing scene. Like everyone just helping each other. So just a big shout out to everyone. So we in this study group, we normally use the link. We also use Repo as the link as the platform to do the live coding, which I just sent it over the chat. So if this is the first time you use uh, if you use the repo, and then because repo requires a membership, they do require you to sign in with your email account. For this time being, you can also use the collab notebook, which we create. We just like make a copy version from from the repo content, so you can use this for the time being. uh, so let us know if you have any questions opening the notebook. Stephanie is fixing the Slack. So like please let us know if everything is doing okay. You guys like doing the notebook, opening the notebook, no problem. Also, quick two things. If you're doing Repo the first time, you have your account, first time joining in, make sure you fork the repo, which should be on the top right corner, to set so that you can create your own copy. This account contains all the previous meeting problems that we've done, so it's like you can take a look at that as well. For those of you who using Colab right now, Google Colab, make sure you go to the file on the top left corner, click it, and save your copy in your own drive because so that you can start editing it. All right, we're gonna we're gonna give a couple minutes. We're gonna give a couple minutes for everyone to get ready. Uh, I do see a lot, couple questions. Sonia is being very awesome, answering a lot of them. Thank you, Sonia.
Oh, this is
For
amazing.
yes, for any questions that we haven't answered, I can poll. Well, we will be doing it at the end of the session, and I can read out the question, and Chana can help answering.
Yep. Yep. Let me know how you folks are doing. Is this if you want to slow down or something like that, like let us know in the chat. And maybe a couple more minutes, or if we can start, send a thumbs up or like a B or something in the chat. I see some amazing questions. Wow.
That's good. That's good. Maybe we'll wait for 1 more minute for everyone to get it set up.
Awesome. Xiaomi is being super, super cool. Like I'm just looking at the chat and the discussions. So amazing. Awesome. Is now a good time to start? Is everybody doing okay? Great, great, great. Super excited for this problem, actually. Love it. Loving the energy. So let's go. Okay, so we're back with after our water break and some interesting discussions. So let's talk about today's problem. It's a super fun problem and like definitely enjoyable the first time you do it and later on as well. It's called group anagrams. So let's, as always, this is the problem description right out of LeetCode. This is the link to the problem, the LeetCode link. If anybody could drop it on chat, that would be awesome. Okay, so group anagrams, right? Given an array of strings, strs, group the anagrams together. You can return the answer in any order. Very interesting. Anagrams. What are they? So an anagram is a word or phrase formed by rearranging the letters of a different word or phrase, typically using all the original letters exactly once. In a nutshell, what does that mean? So if you have like maybe if you have a word with like 4 letters or something like that, an anagram is basically scrambling those and putting them in different positions and different directions and stuff. So if you have eat, an anagram with that of that would be TEAT. And the one thing within anagrams is that if you have maybe two maybe 2 E's or something like that in your initial word, even the anagram should have the 2 E's. So basically, you should have the exact number of letters from the original word to the anagram in different positions or anything. The positions doesn't matter. Whether it's a word or not, that doesn't matter. But it will be an anagram if it satisfies this condition. So let's talk. Oh, wow. Okay, so let's talk more. Like we were talking about, right? An anagram of 8 is TAE, AET, EAT, TEA, and so on. So basically, scramble the original word, put them in different positions and stuff, and you'll end up with an anagram. And also, it's obvious that the length of the original word, it should be equal to the length of the anagram. So, and it should have the same number of letters as well. So I'm pretty sure at this point you sort of understand where we're going here. We have this is our input strings. It's a list of strings. So you have et and so on and so forth. Basically our output should be to group the anagrams together and return the answer in any order. So what does this mean? Like result equals group 1 or group 2. What are these groups? So you have eat, right? What is an anagram of eat? It's T. And what is an anagram of T? Or like what are these groups? So eat, T, 8, right? What are some other anagram groups that you see? Drop it down the chat. Awesome. Awesome. Yeah. So basically, this is you sort of get the gist of what we're doing here. That's it. That's the entire problem. Do we have any other questions about like how our input should be, or like so far it looks like it only has lowercase English letters. So like, do we have any more questions pertaining to that or something like that? Just drop it in chat. Okay. So we can we'll drop all your questions or anything. Yeah, okay. Case sensitivity, empty list, amazing questions. We'll jump into answering all of those questions in the REPL in just a second. I'll have all of these in mind. Awesome. So let's code, right? At this point, we're going to jump to our REPL. Usually how it happens is we go over there and then we talk about the problem a little bit more. And then, we look at some more examples and stuff like that. I'll stop talking and let's go. Okay. So basically, this is just like how I've arranged this is these are the previous sessions for our LeetCode study group. Binary search, greedy approach, hash tables is what we have now, sliding window and 2 pointers. So these are the folders, and then I usually call them in main.py, instantiate, just call the method that we want, and then I pass in the examples here. If you have any weird, I seem to have pretty like normal examples. We'll discuss the prerequisites or like the conditions for this problem as per LeetCode once more, and then if you have any examples or something, post it in the chat. We'll evaluate at the end. Okay, so these are the conditions that that are there for this problem. Your strings array, your input, it only contains lowercase English letters. This is super simple. Like if it becomes this easy, then that's it. Yeah. So that, and then your strings, it can have basically like it can be from 1 through 10 power 4. That's the max. And then your strings of I, which is every single, so like this. This is a string of I.
Sorry, Shannon, could you zoom in a little bit?
Oh, yeah. Thank you so much. I forgot to ask. I'm so sorry. Let's see here. What is the font size? Let's try huge. Is that better? I'm going to move this away so that we get more space. Is that better, everybody? Okay, awesome. Just checking chat once more. Great. Okay, so this entire thing is your strings array, and then this is strings of I. So we can have like an empty like this, like this is an example where strings of I is 0, but the length of your strings is 1. So that's what I've written here in case you're inferring later and stuff. So these are the conditions for this particular problem. We're going to look at a couple of examples here just to sort of make sure to understand where we're going with this. And if you have any kinds of examples or something, just drop it down in chat. I'll check like at the end once we go through this. Yeah, so strings equals this. Okay, so and the result is going to be it's going to be a list of lists of strings. So like eat, tea, and 8. So they'll be grouped together, and this is group 1, right? This is what we were talking about before, and then tan and nat together, and then bait to bait. What is bait? Bat. Okay. So all of them together. Okay. And then if this is your input array, what is your output? Your output is just going to be an empty, a list, but like an empty one at that. And then if you have a single element, like a single word, then it's just one group, right? So you just return that. If you have a single letter, that's just one group as well. So you're going to return that. Great. These are a couple of examples that we have going on. Let's talk about approaches. There are a lot of ways to solve this, but these two that we're going to talk about are some of the most popular and the most like intuitive ones out there. So we're going to talk about both of them use dictionaries, by the way, but they have a little bit of trade-off, in terms of time and space. Like we'll discuss that in just a second. So the first one, we're just going to call it sort and compare. So basically what we're planning to do is this, right? So this is our input array. I think this is okay. Yeah, should have just gone with that. Could still go with bait, but whatever. You take each word, okay? You take each word and then you sort the letters in it, okay? So if you have E-A-T, what is E-A-T? Sorted E-A-T, okay. E-A-T. Need to remember the alphabet a little bit. Okay, and once you sort them, you basically add that into your dictionary like this, your sorted word, and then the word before sorting. So now EAT is sorted as AET, and then you add EAT over here. Simple, cool, okay. Next one is TEA. Okay, what is TEA sorted? It's AET. Great, and AET seems to be in the dictionary already, so we just add it to the next we just append it to that same group. So TEA. Cool. So we're now at 10. What is the sorted thing of like what is 10 sorted? So it's ant, right? ANT. You don't see it here. You'd first look up first for that particular sorted thing within your dictionary. You don't see it there. So you add it. Now you've added it, and then you would add that word, so the sorted word, and then the word before sorting. Okay, so you'd add in, where were we? Okay, 10. Now we are at 8, right? Sorted, you'll get to AET, and then you'll have to add that here. That would be ATE. Now we are here. Again, sorted, you'll get ant. You get the drill at this point. Just gonna fill that out. And then BAT sorted is ABT. It is not in the dictionary at all. So we add it, and we add the word as well. And ta-da, we're here. Like that's it. This is the approach, literally. So okay, we have this beautiful dictionary here. So what do we return at the end? We just return the dictionary's values, and then we got it. That's our solution, right? So it's pretty amazing when you like go over this little by little. And you can return the answer in any order. So that's awesome as well. Great. So now let's talk about time and space are important. Like this is super important to continue, right? Any idea about, any idea about the time and space complexity for this approach? Please drop it in the chat if you have an idea. Of N, okay. Yeah, to start off, yeah. Okay, any more answers? I'm gonna give it like 10 more seconds. Depends on the sort. So the fastest sorting algorithm, I think it's n log n. Python's timsort, I think, and it's called, yeah, it is timsort, and it's Yeah, but Tim sort is like a combination of merge sort and another sort that I am not getting in my mind right now. But even that is like n log n. Okay, so let's talk about this. Basically, one thing we all know for sure is that it's O of n first, right? You're going to do like an entire pass because you need to find the anagrams for everything. Basically, you need to group everything in your strings. Okay, first things first, we'll just add that in there. So that's O of n. Now, what is one more thing that we're doing every single time? Some folks said n squared. So basically, you're taking, like, you need to consider the sorting part of this. Like, you're going through the entire array. That's cool. You're taking each word and you're sorting it, right? Because you sort it, you have another overhead of like n log n, but like n is used to depict the entire array. So let's call it maybe m or something. Yeah, and then yeah. So imagine m is the maximum length of any particular word. Like here, everything has three, and three. Oh, that's why I put in bait. Okay, so this is 4, right? If this is 4, that's like your maximum. Like you need to basically take the sorting into consideration. So when you sort a word, that would be another overhead of n log n. So in this case, if we're trying to do m, right? So that would be m log m, m log m. What is wrong? Okay, I'm not able to type properly. So basically, that would be your time complexity, n times m log m, or whatever you call your variables there. So the entire pass plus each word you sort it. So the sorting that you need to consider that. So that is going to be your time complexity. You're not you're not taking eat and comparing with t, eat with tan, eat with eight. You're not doing it that way. If you do it that way, that would be n squared, I think. But what we're doing is we're taking each word separately, sorting it, adding it to the dictionary, taking the next word, sorting it, basically just appending it to whatever group was there in the dictionary. So that is your time. What about space? Any thoughts about space? Anybody see this huge but beautiful dictionary here? Yeah. So basically, if you're going to be super particular about like space, like in general, it's O of n. But if you want to be extremely, I don't know, particular about it or something like that, then it would be O of n times every single, like the sorted thing, the thing that you have in your dictionary. So it's going to be O of n times m, which would be your total. Like this is your O of what is that? This is going to be your entire list, right? Like your entire strings list, and then these are like your sorted strings or something. So just to remember, it would be like O of n. Definitely, you could go with that, but a much more I think something to think about would be to also mention that you're storing the sorted, the sorted list as well. And I mean, each word is sorted and then you're storing that as well. I'm just going to write it as O of n, but just think about it. It would be, if we're considering that, that would be O of n times m, uh, for the entire list and for every single word. I mean, every single character in the list. Okay. So now that we've looked at that, uh, what is one thing we can cut down on, right? The sorting. The sorting, you can do it, but there's a much, like, I'm a fan of this particular, like, the next methods, like, you know, the most important part of the next method. So that's computing a character array uh, for each word and then comparing. So when we look at character arrays, um, I'll talk about that in just a second. Actually, like, showing is better than just talking about it. So uh, just ride with me on this one. We'll get to the time complexity again, and then you'll see that, like, we definitely, we can definitely go with this approach more than the first one, just because of the time complexity. The space is the same for both, but yeah, because we're storing it in this results, like, dictionary that has the entire list, and then the maximum length would be like M. So yeah. um Within this, you'll basically take each word, and you will find out the character count, like, tuple representation of that word. Actually, array. I'm going to say array. What does this mean? So because this only works when you have conditions like, oh, I'm just going to have lowercase English letters and for this problem. In cases like that, you could basically just start with a 26 length array, entirely initialized with zeros. Okay, start with that. And what we're going to do here is we're going to go over the entire word, and basically ordinate. What it does is it takes a Unicode character, like a letter in this case, and it returns, like, the Unicode code point of the character which we pass in, right? So if you, in this case, you have ordinate of maybe E or something, and then ordinate of A. Like, what I mean here is that you take a word, you get the counts of each letter in that word, and then you'd put it at some position within this character array, which is just completely beautifully laid out here. So how do you decide where to put it? That is where this part comes in. So you can offset, you could calculate the offset like this. So ordinate of E minus ordinate of A. Ordinate of E is going to return 101. Ordinate of A, like, we're always going to start with lowercase a, because that is the starting point of, of like the lowercase alphabets. So it'll be 97 for small a, 98 for small b, 99 for small c, up until small z, which is, I'm not sure which one that would be, but it would go till there. You will start offsetting by that, and this is only 26. So if you do ordinate of E minus ordinate of A, you end up with 4. So in our 26 count array, you'll basically seek 4, and then you'd insert there. You'll increment that is the point in the array that you'd have to increment by 1. So 0, 1, 2, 3, 4. So this was initially 0, but we're looking at E for eat, maybe like the first one, right? We compute it. We basically increment the count of E, and then we're going to do it for the rest as well. So that's how we compute the character array situation. And then after that, what we're going to do is we're going to, actually, let me show it. Okay, so I'm just going to type it as character count 1. For now, for the first one, you're going to take each word, you're going to compute the character array, character count array, and then you're going to basically add this word wherever that you're going to add that character count array thing if it's not already present in your dictionary, and then you'll add in the word for it. So for example, we find the array for this one. And then we would check here initially, it wouldn't have been present in the dictionary. So we inserted it over here. And then we add the word here as well. Great. So next we're going to do it for T. We do the same thing. We'd find that character count array. It's obviously going to be equal to this. So we add it here. Oh, before all of that, why are we doing it as a tuple instead of an array, right? Like, because I'm talking continuously about doing something like this, and the weird thing is we're basically just converting it into a tuple. Why? If you have a list as a key, keys are mutable, so their state can change, and because their state can change, they're not hashable. So if you try like go ahead and try to have like a list and then try to have that as key and then add your value or like whatever to it, it's going to throw you a type error saying key type of key list is not hashable or something like that. And you don't want to have mutable things as keys, because you can change it from anywhere, and keys should not be changed. It just doesn't make sense for a key to just change like that. If you have a database or something like that, would you keep changing your primary key, like just modifying it now and then? So it's basically something like that. So that's why we have a tuple. Okay, we had a quick tangent. Let's head back to what we were doing. So we have tan. We compute the character count array. You don't see it here, so you add it here. So we have character count. I can't type. Character count 2, and then you add what were we adding? Tan. Okay. So we were here. Then we see 8. We do the same thing. Compute and add. And then we do the same thing for nat, character count array, and then we basically append that word to our to the character count thing that we found before. So this would be nat, and then you find the thing again. It's not present here already, so you'll add it. If it's not, it's the same thing. If you don't see it, you'll add it as key, and then the next time you see something having the same character count array, you'll basically just append to it. That's it. And this one was a bat. Yeah, it was bat. Okay. Time and space. Yeah, I feel like we have to. I'm so sorry. I feel like I'm talking a lot. So let's quickly do the time and space for this. So it's essentially, if you actually think about it, you're doing O of n times every single word. You're going to look at every single letter in that word. So O of n times your word, your maximum word length, which is going to be or something like that. And we did talk about like time and like the space before, so that's the same here as well. N times m, and then your space is. I definitely think it's even the space here is going to be n times the maximum length of that word, because that's what we're storing here. But yeah, we can talk about that later. So the thing is, the thing here is there would be another aspect to this, why I keep adding 26 here is that for your every single time you compute the character count array and then you add it, basically what you're going to do is you're going to check that if that entire character count is matching something else on the already existing keys within results. If it already exists, then we then we just append to it. If it doesn't exist, we have to add it, right? We have to add that key, which is this. That may take up a little bit more processing time, right? Because it's that particular tuple is going to be of length 26. So, but that's constant time. It doesn't matter. Lookup is always constant time, and this is what I meant by you'll have that tiny little extra constant time, like constant overhead when you're looking up in a dictionary. So this is what I meant. It doesn't matter. It still boils down to n times m. I'm sorry, I'm going extremely quick at this point because I've been talking too much. But yeah. Okay, so now we're seeing we don't have that same the sorting overhead that we had there. We just have this. So do you think this is a good solution to go with? Just let me know in the chat. I can't say the word chat. Can we? It's going to be super simple. Just the concept is difficult, but the actual the doing part of it is super simple. I'm going to wait for a couple more thumbs ups. Awesome. Love it. Love the energy. Okay. Cool. So let's begin, right? So what are we going to start with? We're going to initialize, I'll talk through as I work so that we don't get stuck. None of us get stuck anywhere. So let's call this res. Okay. And I'm saying let's do a default dict instead of a dictionary, because if you've seen default dicts before, they handle key errors, which means if you're trying to look for a key that's not already present in the dictionary, for example here, right, you were you probably you don't have suppose the character count array tuple that you found for this, it's not already present in the dictionary, but when you search for it, if you use a dictionary, it'll throw you a key error. But in this case, this is going to give you a this is going to initialize it with a default value in general. So if you do if you have lists like this, the default value for this is going to be an empty list. Maybe if you're why did I put in a comment when it's already a comment? Oh, okay. So this is going to be an empty list. If you have maybe integers that you want to add as values, your default is going to be 0. If you want strings, you can do an empty string. So it's going to give you an empty string. Basically, it will if you don't already have it, it's safe to use default dict instead of a dictionary in those cases, I think. If you feel like you're going to be ending up in those kinds of situations, right? Okay, and for that, what do we need to do? Because it's from the collections module, from collections, import default dict. Great. Let's go back. Okay. We have collections dot default dict off. We're starting with, we're going to initialize it to an empty list, right? So we can start with list. It's going to give you an empty list at this point. I mean, you won't have anything at this point. Okay. What should we do next? Let's go back here. We're gonna iterate through the entire strings, your strings input, and then you're going to take each word and you're going to compute the character array count, the character count array. I can never say that properly, even at the end of the session, but we're going to compute that. We're going to check the way we did here, and then we're just going to return. Okay, let's quickly go ahead and do that. Okay, so for let's just say word in strings, we're gonna call it character count array. Cannot type. That is going to be, let's just write a helper for it, right? Find character count of the word. Let's just have it in there. We haven't filled it out yet. We're just laying down the blocks. Okay. And then what we're going to do here is, after that, you're going to this is an array. This function will return an array. So we're going to convert it into a tuple, which would be your key, right? So character count, array. And since this is a list, the first time it'll be an empty list. And if you're adding more things to it, it's just going to be like, you're just going to append it to the list. So dot append of your word, the word that you want, right? Okay. And at the end, what do? We just return results dot values. Values is what you want because that's what looks like this, basically. You just need to return that. And that would give you a list anyway. So you just return that. Great. So now we finished basically 50-60% of this. We just actually I'm going to call it 80, whatever. So now we just have to figure out how to find this character count. Let's write out. Maybe we could do it here. Actually, we could do it right at the top, maybe. Let's just write out our find character count, and then we're taking our word in, running at this time. Okay, so what we're going to start off with, we spoke about initializing the entire 26 count, 26 length, 26 capacity array to zeros, right? So Python has a really, really fun way of doing this. You just do times 26 and then you got it. So this is a character count array with 26 zeros. Now we're just going to have to loop through each character in your word, right? And after that, what are we going to do? We're going to increment that count. So how do we find that count? Char count of what was that again? Yeah, it's going to be the ordinate of your character minus ordinate of lowercase a plus equals 1. Just going to increment it by 1. That's it. And then you just return char count. And what are we doing here? Undefined name collection. Oh yeah, it's just supposed to be a default. We imported default dict already, so because we imported default dict, we didn't import collections. Okay, so I think this is done, folks. Like, we've literally covered everything. Yeah, so basically this is pretty good. We can just like look at our main to see everything's okay. We have a couple of examples here, and then we have some more over here. We're just going to run it to see that nothing is weird at this point. Ooh, okay, the font is super small and I'm running behind time. So this is basically, you get it. It works. Okay, so we're good with that. I'm just jumping back quickly. Two things, just one thing, quick thing. So the next steps from here, try to look at these two problems. They're very, very super similar. You have a lot of confidence right now at this point to tackle these kinds of things. So definitely look at those two problems and see what you think. Maybe post in our Slack channel or something like that. And yeah, with that, I'm so sorry, but I'm handing it back to you, Karen and Stephanie. Do we have time for Q&A?
We are pretty much at time at this point. We have another minute, so I just wanted to say a big thank you to Chethana and Karen for a fantastic session. Thank you also to Sumya for being a spectacular chat moderator. So big round of applause, everyone, for our amazing team. This is a fantastic session. Thank you, everyone, for joining us today. You were a spectacular audience, and I loved all the constant participation. It was fantastic. We have a lot of amazing sessions over the remainder of the day today, as well as tomorrow. Please check out some of those sessions now. We also have a really amazing networking feature, which I totally recommend trying that out. I I love it every single conference that we have. It's a lot of fun. Please also check out our expo booth. There's a lot of really exciting things happening over the next couple of days. And please enjoy the rest of your time at Connect Forward. So thank you all so much and have a wonderful day.
Thank you so much, everybody. Hope you had fun.
You.
Bye.
Bye.